All right, so now let's talk about performance. We've got this algorithm that works to solve the knapsack problem. Uses a DP concept. It kind of leverages this recursive nature of the knapsack problem in a DP way to solve the problem, right? By systematically building up the solutions to subproblems and then using those to solve larger and larger problems. So what's the complexity? Well, I hope it's obvious that we have an n by w grid to fill out. So the complexity is n times w. Okay, so I'm just gonna write clear. You know, we fill out, or fill in if you're from Britain, an n by w grid. So complexity is big theta of nw. Okay, so it's linear in the number of items for a fixed capacity, or you could think of it as being, or alternatively, it's linear in the capacity for a fixed number of items, or you could say it's bilinear in the number of items and the capacity. Okay, the value of the capacity. We'll talk a little bit more about that in a little bit. But the question is this the best we can do? Right? Can we improve upon this big theta of n times w in a kind of a meaningful order of growth way? So we're using a DP approach. So DP is supposed to be about intelligently solving only the subproblems that need to be solved. So the question remains, you know, we certainly didn't solve any subproblems more than once, but did we solve as few subproblems as we can get away with, right? So did we solve unnecessarily many subproblems? Many subproblems. And it seems like maybe we did, right? So let's take a look. Let's take a look at our DP table real quick and think about which subproblems we actually needed in this thing. So if we look at the last one, that does not work at all. So if we look at the last subproblem, or the last problem we solved, the overall problem, the one with all those green done arrows pointing to it, which problems does that point to? Well, it points directly up, and it points to the left 5 columns and up 1 row. Right? So it points to this and this. Oh, those look great. So those two subproblems that I've now circled in rainbow stars are relevant to the overall problem. Okay? But what you might notice is that there's actually nothing else on the last row, the entire last row, that is relevant to the overall problem. So all of these subproblems were solved unnecessarily. So that suggests we could actually do a lot better, perhaps way better, perhaps an order of growth better, if we just ignored those and only solved the ones we needed to solve. So how would we do this? Well, let's fill out a new DP table and think about exactly which subproblems need to be solved. And we can actually do this without writing in any numbers. So let me show you what I'm talking about. Again, I'm going to pause the video, copy this down, and then we'll be able to interact with it a little bit better. So here we are. I've copied down our DP table now as an empty grid, and I put in grid lines to make it a little bit easier to visualize. And you can see they're not straight because we've got the little aliasing going on here. All right, so what we have is an empty DP table, and we'd like to be able to reason about exactly which subproblems need to be solved in total to be sure that we've gotten the right answer to the overall problem. So what are we going for? Well, we're going for this, right? What we really want is an answer to that subproblem, right? The overall problem. What if we have access to all 4 items and the capacity is 10? So I'll put a star in this to represent the idea that that cell is a cell we need to have a number written in, right? In other words, that cell in the table or in the grid is it corresponds to a subproblem that we need to solve, right? So we can say need to visit or, need to solve. Okay, so the goal is to solve the lower right corner, right? So to do this, what do we need to know? Well, we always need to know something directly above us, right? Every single cell, if it has a star in it, the cells above it need to have stars in them as well. And that's because it's always possible that 4 is not a part of the optimal subset. And we need to know, right? We need to know whether or not 4 is part of the optimal subset. The only way to do that is to go find out what's the value of the optimal subset that doesn't contain 4, right? So we have to know that. That's just done. So that's always going to be true, right? The first principle is that if I ever draw a star somewhere, I also have to draw stars all the way up, right? And so that includes, of course, this. Whoops. Okay. So the other thing I need to know is 5 columns to the left and 1 up, right? Why do I need to know 5 columns to the left? Well, because that's the weight of 4, right? If 4 is a part of our optimal subset, then I need to know the value of an optimal subset that I would have if 4 weren't a part of it, right? So I also need to know this. So I need to have a star here. And oh, by the way, I've just written a star here, so now I have to write a star in everything all the way up, right? Everything above it needs to have a star in it. Okay? All right, so now I know this. Is this all, right? Are there any other stars that I need to know based on the last row? And no. So this is actually very encouraging. I actually only have to solve one subproblem corresponding to I equals 4. Only one, and that's the final problem. So that's a nice place to be. All right, so let's refresh ourselves about what is the weight of item 3. So there's our problem. So the weight of item 3 is 4. So now we can use that to fill in any stars related to item 3. So now let's think about this subproblem. So what does this subproblem rely on? Well, it clearly relies on whatever's above it, but it also relies on something that is 4 columns to the left. So it relies on, oh dear, it relies on this subproblem, right? So we need to have a star here. And oh, by the way, since there's a star there, we also need to have stars above it. Okay. All right, now what else? What else corresponding to 3? Well, let's take a look at the middle star. So let's take a look at this one. So this star clearly depends on what's above it, but that's already filled in. And it also depends on whatever is 4 columns to the left and 1 up. Okay, so it also depends on this. So we need to have a star filled in there. Okay, so that star's filled in, and then of course above it needs to be filled in as well. Right, and so everything above that has to be filled in. Okay, so that's fine. Let's move a row up. So now item 2, again, we need to remind ourselves of the value of 2. So 2 has the weight of 2 is 3. So now if we're looking at this row corresponding to item 2, for each of those stars, we'll need to move back 3 columns and then 1 up. And so what does that mean? Well, it means going here, okay, and then everything above that. All right, and then for this one, we have to move back 3 columns and then 1 up. So we have to go like this, 1, 2, 3, right here. So fill in that star, and I'm gonna stop drawing all the arrows. We need a star there. And then for this one, we need to go back 3 columns and up 1 for it as well. And so that'll put us here, and then a star above that as well. And now let me get rid of some of these red marks because they're getting terribly messy. All right, so that's everything corresponding to 2. Right, now what about item 1? Well, with item 1, there's not a whole lot to search for. We do need to think about what is the weight of item 1, just so that we can be sure we've got the right things in the top rows settled. So the weight of item 1 is 7. And so now we can go down here and say, okay, item 1, if I start here, I have to go to the left 7 columns which puts me into the 3 column. And everything above us is already filled out here. So we're kind of done. We're done here already. And then I also have to think about this one, right? So this one and then left 7 columns puts me in the very top left. And so I technically do need a number filled in to the very top left. Okay, so the stars that I've written in this table correspond to the only values we need to know. So if we know all the values that correspond to stars here, then we know the answer to the overall problem, and we're done. Okay, so this feels like a really smart thing to do. Like, this feels like it could save us a lot of effort. So this is a technique that we can actually implement in an algorithm using a concept called memoization. So the way we'll do this is we will implement this recursively, and you could implement it recursively or you could implement it iteratively, but in either case you have to think about algorithmically starting here. And so what you'll do is you'll ask, hey, what's the optimal value for this spot? And what your algorithm will do is it will say, well, the things I need to know are the optimal values for this spot and for this spot. So I'll go into my table and I'll check to see if those problems have been solved yet. If they haven't been solved yet, then I'll solve them. Okay, what does it mean to solve them? Well, it means to check 2 more numbers, right? It means to look above and to look to the left and above. Okay, and so it'll continue to do this process until finally it lands on one of the things it already knows, on one of these base cases, that either the first row or the first column, and then it will kind of bubble back up the recursion to give us the answer. So again, I am going to pause the video, write the pseudocode for an algorithm that implements this, that implements a top-down approach, an intelligent top-down approach to the knapsack problem, and then I'll discuss kind of how it works. So the way this works, sorry for that glitch. All right, so the way this works is a technique called memoization. And so what this means is that what we're going to do is we're going to do a recursive approach to the knapsack. The recursion will start here, and then it will recurse, through the graph, solving problems as it needs to. And then when it goes to solve a problem, first it will check to see if the problem's already been solved. And this is how it will avoid solving problems too many times. So the reason it's called memoization, which always feels like a misspelling of memorization, is that every time we solve a problem, we write a memo to ourselves, memorandum or something to ourselves in the DP table that says, look, now we've solved the problem. Okay, and so this is also called memoizing, which also feels like I'm just using baby talk to say memorizing the answer to the subproblems that I've already solved. And so maybe Levitin doesn't like the term memoization, so he calls this memory functions. And so this is essentially the Levitin implementation of memoization, or a top-down approach to knapsack. And here we call it top-down because we start here at the final problem we want to solve, and then we work our way back to these base cases, these known results. All right, so the memoization approach goes like this. It's very straightforward, right? It makes perfect sense once you sit down and think about it. We initialize a global array, the same size array as before, same size and dimension as before. We call it F, and it has the same purpose as it had before. We put zeros on the first row and column, and then we put -1s elsewhere. So a number that is non-negative means we know the answer to this problem. A number that is negative means we haven't found the answer here yet. Okay, so we'll just use that as a flag that says if we find a -1 in a spot where we need, then that tells us we need to go solve this problem. Right, so then what do? Well, we've got global variables, values, and weights, and so the basic kind of core algorithm works like this. Put it there, keep it off my face. So when we are asking, what is the value of an optimal subset at using items 1 through I at capacity J, the first thing we do is we go and check to see if it's solved. So here we're asking, is it solved? Right? If it happens to be that there is a non-negative number in this thing, then this if will fail, and we'll jump right to the end, and we'll just return the value that's sitting there in the array. Okay? But if we find a negative number in the array, that is, we find one of these -1s that we initialize the array with, that means we haven't visited this place yet, and so we need to go solve the problem. And so all of this, then, is exactly the same, precisely the same as what we had in the original Knapsack implementation, in the other pseudocode. So this is the same logic as before, right? And the only difference is that when we find the value, right? In other words, when we'll make these recursive calls on memory function Knapsack for the problems we need to find. When we find that value, we store it in something called val, and then at the end we put val in the array, right? And so this is a way of saying, for future versions of ourselves, look, we know the answer here now. You don't have to solve it again. Okay, so this is just it's just a complete implementation of the description, the thing I described a little bit less formally up here with the table and the stars. So it's worth asking, of course, did we really save ourselves any effort here, right? So, the question is this better than the bottom-up approach? Is this better than bottom-up? And, in one sense, of course it is, right? It's better because we have these huge swaths of the problem now that we don't have to solve, right? All of this now is not, those are going to remain -1s as the algorithm proceeds. So that's very encouraging, right? That looks really good. But the question is, can we actually get an order of growth speed up relative to the bottom-up version? And it's not totally obvious just looking at it that we can't, but it turns out the answer is that we can't. So yes, in terms of runtime, but no in terms of order of growth. So why is this? Well, one of the ways you can think about it is, suppose I have this grid. Let's think about this very, very abstractly. In the homework, you're actually going to plug in some numbers and think about how to make this thing bad. But suppose we have a grid. Let's think about how we can take the memory function approach, or the memoization top-down approach, and make it as slow as possible. So we know for sure there's going to be a star here, and we know that will fill stars above, right? So there's always going to be stars there. So how can we make this fill in as much of the grid as we possibly can? Well, we could think about saying, look, maybe each item has a weight of 1. Right? So what happens if each item is a weight of 1? Well, then we're also going to get something here, and then the stars will fill in. And then maybe this item has a weight of 1, and so then we'll fill in these stars here. And then maybe this item has a weight of 1, and we'll fill in these stars here. And what we'll end up doing is filling in about half of a grid. Okay, so notice we can fill in up to half a grid. Okay, and notice there's no way to guarantee that half of the grid, right here we've only filled in half of this grid and we've left this entire thing empty, but there's no way to guarantee that the half that we do fill in isn't the whole grid. Right? If our original grid starts out square, then we've filled in half the grid and we've had an order of 2 speed up, which isn't good enough to get us an order of growth speed up. But then even in this case, where we fill in half of half the grid, we have at best an order of 4 speed up. So it's worth thinking about it, worth working this out in kind of detail to think about, why we can't get more than a constant factor speed up. But it's essentially captured in this picture. In that, here we've filled in about a quarter of the total slots in the grid, But a quarter of n times w is still, it still gives us an n times w order of growth. So no matter what we do, right, no matter what n and w are, we're not going to get better than an order of growth speed up using this top-down memoization approach.